Hey class, here's a video on the last part of chapter 12, which talks about nuclear waste. We talked in class about how to generate energy and how to generate electricity specifically from nuclear fuel, and this is all about the waste that is generated after that process and how this is one of the major drawbacks of nuclear energy. So you can see here the full cycle of the fuel cycle of uranium, where it starts off in mines, and you get the enriched uranium and its use in the nuclear power plant, which then generates. So basically, here are all the different types of waste. And here's another, like a picture of the one that we used in class of the fuel cycle, also starting with mining and then the refining, and then using it in the reactor and so forth. Okay, so radioactive wastes fall into various categories. There are about 2,000 tons of it produced in the United States each year. And basically after it's used for some time, it can't be, it doesn't produce enough heat anymore to be used. So this is called spent fuel. But the problem is that it still emits radioactivity. And there's high level versus low level radioactive waste, and you can see that here, low level and high level. And we'll have another slide for it, and also low level there and there and there. There's also these tailings, so that's the kind of what's left over after the uranium is mined. And so that's another component of the waste. Okay, so low level radioactive waste, and your book differentiates between the tailings and then low level and high level. But this is primarily, the things that have been exposed to radiation. Okay, so that's either the clothes or the tools, and these are stored in what are called, basically nuclear dumps. So they're kind of put in these containers. They're kind of set aside so nobody can get in touch with them and contact with them. But again, they're low level, so they're not so threatening to the environment and to people. At least it's not as threatening as the high-level radioactive waste. And the high-level radioactive waste is that spent fuel. It's the actual uranium pellets that are no longer usable. It's the water that was in contact with the radioactivity, the assemblies, the fuel assembly rods, basically all the equipment that was in direct contact with it. Okay, so as as we talked about half-lives and stuff, once that uranium is used, it's still going to be radioactive for thousands of years because it has such a long half-life. So this is really dangerous for the environment and for human health, because these atoms, they're emitting these radioactive waves, and that can damage our DNA. It can also mimic key nutrients. Strontium, for instance, acts like calcium in our body. Our body thinks it's calcium, so it incorporates it into our cells. And once it damages, the DNA, that can cause cancers and malformations and that sort of thing. So if you look here, what uranium starts off with, the uranium fuel, as we talked about in class, about 3% is the radioactive 235. And once it's spent, the what's left over is about 95% of the spent fuel is the 238, the non-radioactive. But then you have some 1% is the 235, and now these other leftover products are these high-level radioactive wastes. You also have some plutonium, the strontium, just all these different elements that, because the atoms are breaking up, right? So you have this uranium, but once you get rid of some protons and neutrons, it's a different atom, but it can still be radioactive. It can still be releasing those gamma rays, which are very damaging. So the question is, what do you do with this? And this is, again, one of the major problems with nuclear energy is what can you do with this waste, this high-level radioactive waste? Okay, so we talked about the low level being stored in those nuclear kind of dumps. This is for the high level. Okay, so you can put it in pools, or you can put it in these above-ground concrete and steel casks. Okay, very, kind of surreal looking. Okay, so for the pools, they're these spent fuel pools, and if, I'll get to the Japan thing in a second. So these are lined with concrete. They have to be at least 20 feet deep, Um, they have, obviously the water is shielding the radioactivity. So when they go in here, when the spent fuel goes in there, it's called hot. And that's not because it's hot temperature-wise, but because it's very radioactive. And so this is kind of cool it down. And it's only temporary. So in Japan, when they had the nuclear power plant disaster, one of the problems was these fuel pools were heating up, and they didn't have, because the power of the power plant went out, which is kind of ironic, but they didn't have the means to keep the spent fuel pools also filled and cool, which was one of the many issues that were going on with that. Okay, so after it's kind of cooled down in the pools, you then put it into a storage cask. They're stored above ground, and you can see all the insides here. They're all insulated and everything. And again, the fuel can't be hot, so that's why it has to be in the pool first. And again, this is only temporary. At least the plan is for it to only be temporary, because in theory, there's hopefully some sort of long-term disposal option. And there was for a while a site proposed in Yucca Mountain in Nevada in 1978. And it was very controversial, obviously, because nobody wants a permanent nuclear waste dumping ground near them. And you can see this is kind of a pretty cool diagram here of the kind of the anatomy, basically, of this disposal site. So you have all these different shafts for the nuclear fuel to go down. You have a ventilation shaft. You have one for people. And then you can see down here all this network of tunnels. Okay, so you have 1,000 feet, and that's going to be where all of these canisters would go way underground. So there are a lot of, I mean, it looked like a good site, but, it has to be perfect for it to really clear. And there were some tectonic issues. Potentially, it wasn't that close to a fault, but some folks were worried that, if there was some sort of earthquake that happened around there, you would have a problem because it's so far underground, and there might be some sort of release or explosion or something. So the jury's still out on that. Other options for long-term storage, they cannot have, long-term storage can't include any of these options, which is, problematic. It can't be incinerated or burned, because you just release all that radioactivity. There's no way to safely destroy it either. Shooting into space, not a viable option, because we don't know where it's going to go after that. It could, in theory, come back to us, or same with dumping it on the ocean floor. It's kind of like you want to know where your enemies are. In this case, you don't want it to go somewhere where you can't really control it. And same with burying an ocean trench. So these options would really allow and enable radioactivity to enter into our oceans or the atmosphere, and that's the absolute worst case scenario for us. So kind of where we are now is basically to store it safely on Earth indefinitely, somewhere where you won't get into the environment or into groundwater, because again, those particles are, the half-life is millions of years, so it's going to be constantly emitting this radioactivity. Somewhere that's far from where humans are, in case there are any accidents, and somewhere where the waste can be transported with a minimal risk of accidents or even theft or attack by terrorists. And I'm sure you guys are probably curious, how is this connected to nuclear weapons? So nuclear bombs are about 85% of that radioactive U-235, as compared to 3% of the nuclear fuel in the fuel pellets. So very significantly higher concentration of radioactivity in a nuclear weapon. And they are made using the spent fuel from nuclear energy. And the plutonium that is used to make nuclear weapons is produced from the U-238. So if you go back in the slides with the columns, you'll see that plutonium can come from U-238, and that is highly reactive also. So there's definitely a connection, but you obviously have to go through a whole other series of processes and steps to make nuclear weapons. But that's why when when we're looking at other countries that are enriching uranium, we start to wonder, what are they enriching it for? And then this slide, I just couldn't resist, not in my backyard, NIMBY. Basically, this is the problem with so many things, including, especially when we have our debate in class. Nuclear power is good, and thinking about how much power it produces, but nobody wants to put their waste in their backyard, and nobody wants to have the power plant in their backyard. So where do we put it? And 3 Mile Island, as you guys probably know, was the most serious reactor accident in the United States. It was in Pennsylvania in 1979. 50% of the reactor core melted. Okay, no radiation escaped though. So there was really no substantial damage or casualties or health effects, but it really did, and this was, kind of early in the environmental movement, it really did heighten people's apprehension and awareness for nuclear energy and led to the canceling of many U.S. Power plants. So it wasn't, there weren't actual effects in terms of the science, but socially there definitely were. And then there's Chernobyl, which the accident was in 1986, the worst accident in history. And here's a picture here of the explosion. So the nuclear reactor actually exploded, and it released tons of radiation out into the atmosphere, spread across large portions of Europe, got into the water, got into the atmosphere. So you can see here all over the place. It was basically spread kind of in an unpredictable fashion depending on which ways the winds are moving and the water currents. There was high contamination. The death toll is estimated to be between 10,000 and 100,000. Again, that's quite a range, and it's just hard to determine. Short-term or immediate deaths are very easy to pinpoint the cause of, but if somebody dies 30 years later from cancer, it's hard to determine if that was, from the accident or not. But we saw later lots of birth defects. So any woman who was around that, at that time, and her gametes her eggs get mutated, and the DNA gets messed up, then they're going to have children with birth defects. Lots of cancers, mental retardation. I was Google imaging and found this poster, which is so sad. So we think about the pros and cons of nuclear, and we have to think of these. It's very rare for an accident to happen. We have nuclear energy happening all the time, electricity being produced all the time, but it's, it's tough. It's a tough trade-off. So I want you guys to think about the pros and cons for yourself and really think, what would you argue for, against, under what conditions, and the debate we have in class will really get to that as well. It's a tough issue. And then there's also fusion, so kind of the opposite of fission. It's the reaction that powers the sun and other stars, and it's basically when nuclei are forced together to produce a heavier nuclei, and heat is released. Okay, so you can see here we have 2 atoms coming together and they fuse, so fusion, and that releases a lot of energy. So it's promising in that there is a lot of energy release when you have this. Hydrogen is the main fuel for this. But the problem is, so you can see this is hydrogen, 2 hydrogen are coming together to make helium. But the problem is that the heat that is used to make this happen is 10 times as hot as the sun, which you can imagine is probably a little bit problematic when we're trying to have that process happen on Earth somewhere. So containing that heat is one of the major limitations of fusion power at this time. And lastly, there's another type of fuel aside from uranium that is also able to produce nuclear energy, and that's thorium. And its atomic number is 90, and the atomic weight here you can see is 232. And this is a naturally radioactive metal, can be used as nuclear fuel. I have 45 seconds, so I can do this fast. Advantages over uranium fuel: it's 4 times as abundant as uranium. The meltdown is unlikely since nuclear chain reactions, they can't be sustained, unlike uranium. It's not easy to weaponize it, and the radioactivity is significantly lower, and it can be used as a fuel without enrichment, so you don't have to go through that whole process of enriching it, so you don't have the waste and production costs that you do with uranium. The disadvantages, though, we still need a lot of testing, licensing, infrastructure, startup costs, and you do have to deal with the waste because it's still there even though it is less. And projects are underway in China, India, and Norway. Thanks, guys. Bye.